Welcome to the MTL seminar. Today we have a joint with the Medical Electronic Device Realization Center, the MedRC. So some of you from the sort of medical world are here joining us in MTL. It's a pleasure to introduce a longtime friend who I've known since probably when he first came to Berkeley. I was around out there, and Jan Rabai. Let me give you some of the details here of Jan. He's founding director of the Berkeley Wireless Research Center and also Ubiquitous Swarm Lab. He's been on the forefront of many groundbreaking innovations, especially in low-energy design, and is currently exploring the interaction between information technology and neuroscience. Jan is here on sabbatical, spending a few months with us. And I encourage you to try to stop by and see him once in a while. He's got a boatload of great ideas and is an interesting person to talk to. So with that introduction, Jan, please tell us about a roadmap to long-term brain-machine interfaces.
All right, good afternoon. Thank you, Charlie. It's a pleasure to be here, and actually I've been enjoying my couple of months already here in Cambridge. Been great to be away from the typical Berkeley hustle. So what I'm going to do today is talk about some of our work we have been doing over the last 5, 6, 7 years or so in the domain of brain-machine interfaces. Now, before I go into the detail there, I just want to kind of present a little bit of my philosophy of how I do research. Typically, a lot of the research projects we're trying to do, we start basically with a question. Question that says, what if? Type question. And then we start working it out. I call it the reverse time machine approach to research. You kind of go forward and then you figure out here's the vision, and then you work backwards and figure out what are the kind of key technologies we have to address to make that vision happen. Before I go there though, I have to acknowledge a whole lot of people who have contributed to this presentation. A lot of work is done under part of something that's called CNEP, the Center for Neural Engineering and Prosthetics, which is a joint venture between UCSF Neurosurgery, UC Berkeley Neuroscience, and Berkeley Engineering. So here's a question that I've been asking myself since the last 7, 8 years or so. What would happen if we can start build electronic sensor nodes, sensor communication nodes, that become so small that they actually become the size also of a basically biological cell? What could we do if we have that capability? So this thing is definitely not out. The question itself, at the time we asked it 8 years ago, 9 years ago, was kind of far out. But now if you look what's happening, you see many, many pieces coming and falling into place that says, hey, this is happening, this is possible. And I just quoted a couple of things here, like just 2 weeks ago, some folks from Columbia University published a paper on basically a radio transmitter, 33 gigahertz, which is a couple of nanowatts and is indeed the size of a biological cell approximately. And there's a whole bunch of other things, pieces falling into place in terms of power generation, energy generation, computation, all those kind of things are happening. So this is not out of the ordinary in terms of a question. So going back to the original question, what could you do, right, if you would have something like this? And a lot of my inspiration in how I get research done, I typically get from one particular source. It is science fiction. I read all those books and I said, wow, this is a really cool idea. Could we do it? Or what would it take to make it happen? And I just give you a whole bunch of examples here of people who have examined how really tiny electronics could indeed happen and interact, let's say, with the human body. So there's many options. But the one that excited me the most was the following one. It says, what would happen if I indeed can use those things to bridge the gap between our biological computing world, which is our brain, and the physical computer world which is out there? Could we basically bridge that gap using this type of electronics that we're creating? So scaling the brain cyber barrier is something which is an interesting challenge. Now, if you could do so, what would you enable? Well, there are many things, right? Obviously, if I could link my biological computer to the cloud out there, I can come up with some very interesting applications. And people have been building a variety of applications around that, basically brain-computer type of interfaces. All of them primarily based on EEG, fairly rough signaling, But people have shown that you can actually drive wheelchairs, you can play games, you can do all kinds of interesting things. Still primitive, but it shows you what would be possible. Now, to make this for real, to really have tight control and have a wide bandwidth connection between the brain, we still have some time out. It's not going to happen instantaneously, but we're putting pieces into place. In the short term, though, the key focus is not on the general type of computing interface, but really think about addressing neurological diseases. One of the biggest areas of basically healthcare and health costs these days. Many things you can do. Obviously, we have a large population of folks that have strokes, have spinal cord injury, you have depression, you have traumatic stress, all those type of things are diseases that basically impact a lot of the society today, and where we might be able to do some things. So you might have heard about the whole world of neuroprosthesis, where we have a neural interface and you use that to drive a prosthetic arm or a leg for somebody who's paralyzed. And some enormous success has been reported by a variety of schools, Brown, Pittsburgh, and so on and so forth, have shown really amazing things in that particular space. So very important area, definitely also for the defense community today, spending a lot of money on that. We have soldiers coming back from Afghanistan, Iraq, basically missing limbs, and they're trying to basically address some of those things. The other area which I think is not as straightforward is the area of neurorehabilitation. Somebody has stroke. Stroke basically destroys part of your brain and you lose functionality, right? Motion or speech or something like that. Very often, the brain adapts. Actually, it remaps some of that function to neighboring regions very quickly. Or it doesn't happen at all. In some cases, it doesn't happen at all. People stay paralyzed or basically cannot speak anymore. There's this area of rehabilitation where you try to help the human to remap the function by using, for instance, exoskeleton. So if your hand is paralyzed and have an exoskeleton that makes it move, it might help me in basically remapping that function. Now, if you do this blindly, it basically doesn't result in, it's kind of a dark shot you basically are taking. However, if I have the capability of interacting while I'm doing this, having signals from the brain directly connected to your exoskeleton, you can accelerate the whole process of neurorehabilitation. And then I already mentioned there's a whole bunch of neuropsychiatric diseases that people believe that BMI, brain-machine interfaces, through a combination of readout and stimulation can help to address. And I already mentioned depression and traumatic stress. So how does BMI basically work? Brain-machine interface is basically a closed-loop system. So somewhere we have the brain, and we try to get some signals out of the brain. Measure what the brain is planning to do, what the different activities, where the activity is, and how it basically. Those signals get acquired, and then you turn them into something digital. By having a sensory front end, we do some acquisition hardware, all those kind of things. And bottom line is we get some digital stream coming out of here, which we then clean out. Because those signals, as you will see, are kind of noisy. They're basically very variable. You do signal processing, you do some artifact removal, and then you feed them into a control algorithm. A control algorithm that says, now I have those signals, what is the action that's basically intended? I want to move my arm, what basically are the parameters I can track from that to help me to move that arm? And ultimately, this may go over a wireless link, or might be directly, but actually you go to a mechanical actuator, which could be your artificial arm, for instance, or a stimulation device, which can move the arm, as you see in this particular case. Now, this thing wouldn't work at all if you wouldn't have anything extra on that. If I just would have an open loop neuroprosthetic system, basically, that thing will basically flounce back and forth and basically have very little chance of operation. The key thing that makes it work is the other part here. The human body is in the loop. It basically observes what's happening through visual feedback, or basically tactile feedback, or any type of feedback, or stimulation, per se. And it adjusts. So it's an example of two adaptive systems. You have an adaptive controller, and you have an adaptive type of system here that basically the brain basically relearns basically pathways while you're basically performing the tasks. It's pretty amazing how fast the things work and how well they work in actual circumstances. So this is the paradigm. So what I'm going to focus on primarily is how to make this thing happen in such a way that I can do this thing for a long period of time. Right? All the things you see today very often are stunts. Basically get implanted, they get work for a little bit, and then basically the reaction dies off and the thing doesn't work anymore. So question really is how to interface with the brain. How can you read out brain signals effectively? And there's many different ways that people have come up with, in a variety of waveforms. Basically, you can think about magnetic resonance, fMRI. Right? Basically, it's a very often used type of tool. It's a big machine. It's not something that easily you're going to carry around with you, but it gives you some nice resolution type of idea of activity in the brain. There's a lot of talk about optogenetics these days, where we use optical interfaces, where you have genetically modified neural cells, and we can turn them on and off using light. Very big area. We can even maybe think about molecular. There's sound interfaces as well. Ultrasound is another area where you actually can use to stimulate and measure signals. But the most prominent way today is electrical. That's really what we focus on. Every time a neuron fires, there's an electrical waveform that if you put an electrode in that neighborhood, you can measure that waveform, and bingo, you got that activity happening. Right. So that's what we're going to focus on, because I think any practical system today is going to be based on that. I'm not saying it's going to stay like that in the future, right? So how can we do that? How can we measure electrical signals? Well, again, there's a number of ways of doing those. If I just want to be minimally intrusive, what I can do is put some electrodes, and some of you already had it when you had a little accident, you have to go to the hospital, you get an EEG. You put some electrodes on the head, and you measure some electrical waveforms. Now you have to be aware, as you can see on this picture here, the electrodes are fairly large. The brain has billions of neurons. If I now basically put a large electrode on there, what I measure is not a single neuron, but an ensemble of neurons. Basically the combined activities of neuron firing in synchronicity. You get waveforms, alpha waves, beta waves, gamma waves, delta waves, right? That's what you measure, that's what you can see. Now the problem with this is it's kind of nice, right? It's not that hard to do. You can build very nice, good-looking headsets that do these things quite decently. The problem is that the skull, this basically is in between your sensory and your source. Right? The skull basically does two things. It's an attenuating factor. You have a lot of loss when the signals go to the skull, number one. And number two, it's a low-pass filter. So anything that's above 50 hertz kind of disappears. Now it turns out if you look at the waveform, those low frequency waveforms that the brain produces, when you do something, actually the activity tends to shift to the gamma waves, which are typically 50 hertz and above. So all those things are basically filtered away, and the only thing you can see is the lack of energy, not the presence of energy, as you would see with the gamma waves. So that's the problem. Maybe we can get better in signal processing, we can do better things, that we can get better signals, but today it's really hard. So if you want to get anything which is the resolution, basically gives you a decent signal, you have to go below the skull. And the way you do that is something which is called ECOG, electrocorticography, which is the same thing. It's exactly the same idea. You put electrodes that are connected together on top of the cortex. And you measure, again, these low frequency waveforms. The nice thing about this now, I can make this thing smaller. Right? The resolution can get better. That's one. Number two, that low pass filter is gone and the attenuation is gone. I get better signals. And I get signals that can go up to 300, 400 hertz approximately. So you get more data. Oops. Let me go back. All right. So that's that. Still, however, every one of those things you measure is the results of thousands to maybe 1 million neurons firing under that electrode. So it's combined activity. If I really want to poke down to the small resolution, what I have to have is electrodes that basically can get close to a single neuron and measure that single neuron firing. And the only way to do that is indeed having to have penetration. Today, you have penetration, you have little needles, electrodes that basically penetrate into the cortex. Cortex is about 2 millimeters thick, so they're basically 1 to 2 millimeters long. They have a bunch of electrodes on this, and they get in the proximity of neurons, and they measure indeed local action potential, I would call it. You can see the neuron firing, as I'll show you in a minute. So All of those are of interest. You actually can get a lot of data from this global information. You can get a lot of data from individual neurons. If you want to get a lot of resolution in hand motion and things like that, very often you have to get almost that close to a single neuron. Otherwise, you don't get the resolution that you really need to get. Now, the good news is that the state of the art is rapidly advancing. A lot of people are doing various things in this space. In terms of neural interfaces, you have the cochlear implant is now being used everywhere. I believe there's about 30,000 implants in the US per year on this. There's a bunch of this kind of electrode arrays now that you can buy on the market, the BlackRock ones. There's Intel is selling chips that basically allow you to basically acquire those signals. And Medtronic actually recently, last year, put out first product on the market which is called the Active PCS, which combines both stimulation, deep brain stimulation for people with Parkinson, but it's not only stimulation as they did in the past, they also have measurement. They have a bunch of electrodes, ECOG-style electrodes, that can measure what's happening when you stimulate. Because in the past, they just stimulated and they had no clue what's really going on. So it works, it doesn't work. Right. So a lot of good news is that the state of the art is advancing. Still, we have a long way to go. Because what I really would like to do is indeed that long-term BMI. I want to have an implant that I put in there that lasts at least 10 years. And that has high resolution. Actually, it turns out if you want to do reasonable BMI, I think it's important that we have neural activity measured at multiple scales of resolution, of multi-scale type of resolution acquisition, using both arrays of pattern electrodes like ECOG on top of the cortex and individual electrodes that basically talk to individual neurons. And we want to get this something like that that basically can not only measure but also stimulate, because that's an important part of the picture as well. And it should last for 10 years. So how do you get to 10 years? Nobody can do this today. Well, here's my rules that basically I think that can help you to get to this longer lifespan. Number one, it has to be small. Small is crucial. Anytime you put something big in the body, it doesn't like it. It's going to fight it. And it's going to build stuff around it, and at some point in time, your electrodes won't work anymore. It even pushes them out very often. It has to be compliant, obviously, with the materials in the brain. And it has to be flexible. The brain moves. Every time your blood pumps through, you basically have the thing going in and out. There's micromotion, there's all kind of stuff. If I shake my head, I move my brain. If it's fixed, you have a problem. You're going to damage the tissue. Number two, wireless. If I put an implant in there and I have to have a cable coming to the skull, it doesn't work. I can tell you, I can guarantee you after 1 year, at least, you're going to have infections coming in there. Infections happening. So this idea of having USB interface to your brain, forget about it. Not a good idea. So it has to be wireless USB. And then finally, it has to be robust. Very robust. And the way you get robustness is through redundancy. Redundancy is crucial. It means that don't count on one single electrode working. Make sure you have plenty of them. Redundancy is really crucial. Lots of selectable channels is a very important goal as well. So that's kind of our vision of how we can go to BMI. Now the question is, where are we on that roadmap? How far are we to build some of those things? So I'll give you 4 challenges that I already kind of pointed out to, and then how we basically address those challenges. Number one, as I already said, longevity. And the way to address longevity, and this shows some of the impact of those implants. You put an implant in, you can see that tissue gets damaged. This is not a very nice picture. You have to have this thing sitting on your head for quite a while. It's not something you basically like. And this is some of the clinical, somehow the slide got chopped off on this side right here. This is how actually ECOG is applied in the clinical setting today. They put the electrodes on the brain during brain surgery, and you see those ribbon cables coming out. Not a very good idea in terms of reliability. So key thing is scar tissue formation has to be avoided. Cables cause infection, packaging, all those things are important. So longevity is challenge number one. Challenge number two is that the signals themselves tend to be very weak. Even if I can get an electrode very close, what I'm getting is signals that look something like this. And by the way, this is a measured waveform from a rat. This is a very nice waveform. If you see a waveform like that in true practice, in vivo, you're already extremely happy. Most of your waveforms are by no means as good. So what you see is that your waveform, this is a single action potential waveform, measure close to a neuron using some sensor node. And you see a variety of things. You see spikes. Now the spikes are about 10 microvolt to a millivolt in size. So very small signals. On top of that, you have this slow frequency movement, which is called the local field potential, the same thing as you see in ECOG. It's all the neurons around you that fire and basically synchronize, and they create these waveforms. So you have low frequency and high frequency. High frequency, this is kilohertz, right? It's not like you typically would see in other applications. There's offset, because you put electrodes in, you have tissue in between, there's going to be voltage building up. You have to basically, the offset typically is way bigger than the signal you're measuring. And there's plenty of noise, other noise sources sitting there as well. So trying to acquire a signal like that reliably is a big challenge. So we have low SNR, high offset, mixture of various signals. Situation is even worse when I look at ECOG signals. I don't have nice spikes there. If I look at ECOG, I get this kind of almost noisy waveforms. That's what you see. So where's the information here? And you only can start actually seeing information when you go to the frequency domain. In the frequency domain, I can start binning and look at how the energy moves between bands. That's really what you do there. So challenge number 2 is sensitivity and discrimination of signals. Make sure that you can get rid of the artifacts and avoid them. Challenge number 3 is what I call the data deluge. I told you I want to get thousands of channels. But you have to get those thousands of channels out of the head. You get a lot of data. If I basically take a single action potential channel, 20 kilohertz, 10 bits, it's about 200 kilobits per second of information per neuron that I produce. Okay? And that's what you need to have. You have 10 kilohertz bandwidth, so you oversample it with a factor of 2. On the other side, you have the ECOG channel. There, the bandwidth is a lot lower. I mentioned there's nothing beyond 500 hertz in that particular case. 1 kilohertz times 12 bits, 12 kilobits per second. So I multiply this now by 1,000. You figure out how much data I have to get to the wireless link. Now, the problem is with these wireless links we're going to build through that skull are not very good. It's not your gigabit per second type of data rate. Today, we can kind of easily build radios that go about 1 to 2 megabits per second. And that's going to set how much information I can get out of the skull. So you have the balance between, on one side, the amount of information I'm getting by the very parallel sensory arrays and the information I can get out. So how do you deal with that? So just as a side note here, if I would basically observe every neuron of the human brain at 1 bit per spike, at 1 kilohertz, I get 80 terabit per second. So the brain does a lot of stuff. Well, maybe not all your neurons are working all the time. That's a different factor. So data deluge is number 3, how to deal with all the information that you get in and how to turn that into actual information. And finally, energy. Anything I'm implanting, it has to be powered. And I say I don't want to have cables going to the skull, so I have no power, external power coming in. How do you can get then your nodes powered? Well, batteries are out of the question. It's a long-term implant. I'm not going to take things in and out to replace the batteries. Energy scavenging might be an option. That would be nice, right? If I can get the energy from the body. Doesn't work very well. The only thing that could work maybe is heat, temperature gradients, but try to find a good temperature gradient within the body. Again, you have to go outside the body, inside the body, same problem. The only thing that might be interesting is the same thing as the body does, basically biofuel cells. You take glucose and you take oxygen, you put the two together, and you get basically gluconic acid, and you get electrons, which is beautiful. It's a little battery. The other problem with that battery is today I get about 0.7 microwatt per millimeter cube. Not very much. So the only thing that people know how to do right now is to basically use external power. You wirelessly power the devices. And that's true for most of the implants that are being used today. You basically have an external electromagnetic or magnetic type of source. You transmit it. You basically rectify it at the source. You get some power out of it. And you use that same link to get the data back by modulation, like an RFID node. Right? And that's what we basically are doing. So, but the key thing is that energy is my fourth challenge. So, kind of summarize it, we have 4 major challenges. How can we tackle them? Right? So I believe actually that today is really the nice time that so we have the confluence of all those type of things happening, nanotechnology, micro and engineering systems that allow us to bring and tackle those problems in an efficient way and open really the door for some really true breakthroughs. So we're basically at the confluence of a lot of things happening that make all those problems, those challenges solvable. So just give you an idea here. This is some of the stuff that can be done using microfabrication technologies, right? There's a bunch of MEMS technologies, but also semiconductor technologies that allow us to print very small patterns on a variety of fabrics. It could be in silicon, but it also can be on flexible materials like Parylene or something like that, which allow us to print very low, high resolution, in the scopes of tens of microns, type of electrodes, wires, antennas, and so on and so forth. We can actually make very small probes that are so small, they're about 50 micron in width, maybe 50 to 100 microns, so that they come at the point that they say, hey, maybe the impact on the human body is going to be very small. And this can be in silicon, but it can also be in flexible material. They can be patterned. They can combine light and electricity, so you can think about optogenetics as all those type of things coming very nicely together. And using very interesting fabrication technology, we also can devise insertion approaches. Because obviously, to get those electrodes into the brain, you have to have little machinery that allows you to bring those things in there without performing any damage. So a whole tool of things at our disposition in terms of electrodes and basically deposition devices. The same way, we have basically by using advances in microtechnology, now we can build acquisition systems that are really getting very low power and very small. This includes amplifiers, it includes A to D converters, it includes communication signals systems, it basically includes antenna devices, and so on and so forth, that basically make it all happen. And I just show some examples here. I'm going to put them together in a bigger picture in a minute. So, lots of opportunity here, again, because of progress in technology. So, let me give you some examples of systems that have been evolving and how we're basically moving step by step forward to that big vision that I pointed to you at the start. So first of all, ECOG, as I said, gives you this global picture. It allows you to look at how our activity is moving between different parts of the brain, and actually allows you to infer quite a bit of things. So some of my colleagues at UCSF have actually shown that even by using ECOG, for instance, I can have imagined speech. You put it above the speech region, and I can use that information to almost figure out what you're planning to say and synthesize that. So a lot of things I can do with ECOG. Here's kind of the system vision we imagine for that. This is a broad picture. So using semiconductor technologies, again, patterning technologies, we can use flexible substrates on which I can print very high resolution electrode arrays. Way better than what you saw in the beginning. These are things that are basically at about 100 micron spacing. So you have a whole array of little electrodes, as you can see right here. Flexible, completely compliant with the brain tissue around it. Now, to acquire the data, I put an ASIC device, very tiny, hopefully, that basically takes all those signals and turns them from something which is kind of noisy analog into a stream of digital signals. So that's number two, the ASIC part. And then the third part is to get the data back and forth outside the brain. And the way you do that is, again, using wireless. You have an external antenna that sends the power in and basically powers this chip, and at the same time gets all the data back out. Now, the nice thing about this flexible substrate is that I can print the antenna on the same substrate. As you can see right here, you have the antenna sitting right around the electrode array. So this is the way we get power out in and data out, by basically having those printed antennas. And this is some measurement data. I'll come back to that in a second. So our belief is that you can actually build those platforms with thousands of electrodes. And we can do the electronics to do so as well. This thing is completely compliant, so there's no reason that an implant like this could not stay for a longer period of time, 5 years and beyond, within the human body. So there's some examples of how to build some of those arrays. There's a number of groups working on this. This is University of Illinois. The John Rogers group has building some very interesting things in terms of compliant fabrics. This is work that was done in Berkeley. And as I show here, this is very similar to traditional etching and patterning type of technologies that we use for semiconductor, which is nice. This is a chip we published this year that does the data acquisition. It performs 64 data channels. So what it has is you have your electrode array that I just showed you. We have an array of 64 amplifier front ends and A to D converters. So for every one of those channels, you basically get a digital stream, and then you stream them together and feed them to a radio miller encoder that basically transmits the data out. Same die also does the power collection. It takes the RF signal in and turns it to DC to power the devices. So it has basically everything integrated on one single device, which is about 2 millimeters on the side approximately. Here's your 64 front ends. This is the power management. This is your transmitter. Now, the interesting thing to notice is that this takes about 2 microwatt per channel. That's a number to remember, because if you scale up the number of channels, I'm going to multiply that number. I have to acquire the channels, so 2 microwatt, 1 to 2 microwatt is something we can comfortably do today. If you want to do more channels, you have to deal with that. The channels itself are very small. It's like a 40th of a millimeter square to basically perform one of those things. And the total power dissipation of this whole chip, when fully active, is about 250 microwatts. So very small, something that falls within the realm of the wireless powering. Now, when you think about wireless powering, you basically worry a bit, right? I basically have an electromagnetic thing sitting out there and send waveform to my brain to power devices inside my body. How much power can you transmit? How much is legal? Right? Obviously, there's some very strict regulations on how much power you can transmit. Right? Electromagnetic, magnetic, or whatever it is. So there's a couple of factors you have to take into account. There's limitations on how much you can transmit. And there's a fact also that you can optimize the size of your antennas. As well, you have some loss factor when you go to the skull. So you have to optimize all those type of things together. Say, what's the optimal frequency I should use to transmit that signal? If I go too high frequency, I get too much loss. If I go too low a frequency, I need a big antenna. There's a variety of factors that basically come together. But the bottom line is, if you model these things very nicely, this is a complete 3D modeling of the system, where you have the internal antenna, which is a slotted antenna, maximizes the spread of the electrical field and the heating effects. And this is your internal device. You look at various shape factors. You really do complex analysis on this type of thing, and you figure out that, if between 200, 300, 400 megahertz, you're in a sweet spot. And actually, you can get legally, without having anything, you can get about a couple of milliwatts. Say the power, if you look at here, at about 300 megahertz, I get about 3 milliwatt of power, which is way more than plenty, because I need only 250 microwatts. So I can actually go substantially below what will be legally required, or regulation basically dictates to us. So this is cool. It shows it all can be done. There's no real hindrance in the whole system whatsoever. And this is an implanted system as shown. This is a rat. So you have the electrode array sitting right here. And this is some measurement of the data I already showed you. These 2 waveforms show you what's happening when I do have the rat in different states. In this case, particularly, we just changed the amount of anesthetic state that the rat basically had. You see a shift to the delta waves when you basically go to higher levels of anesthetics. And you can indeed see the shift in frequency between the different bands as observed in vivo. So, cool. Large picture, I think we can do. One challenge, however, as I already mentioned, if I go to this from 64, array by 8 by 8, I want to go to 10 by 10 or more, 30 by 30, 40 by 40, I have a challenge here. I'm going to those thousands of channels, I have my data deluge problem. Now, we know how to do that, right? So, well, no problem, right? I can do compression. Right? If I do compression, I might be able to take a lot of channels and put them together and basically get the data out. But compression loses some of the data. That's one of the issues. The second problem that I have is if I have 1,000 channels, I need to have 1,000 front ends continuously working. At 2 microwatt apiece, suddenly I'm already at 2 milliwatts without doing anything. Right? So I'm basically running into these power limitations when I go to larger channel problems. So interesting challenge is still there. I think we really have to think about what to do here. And one thing that maybe is interesting is basically residing to signal processing. There's a lot of work going on these days on compressed sampling. The fact that the data might be sparse or correlated or a variety of things, there's some pattern you can see in the data. You can use that to reduce either energy dissipation or the amount of data I have to communicate outside the brain. So it's not easy though, because unfortunately this waveform kind of washed out. But this is a number of channels simultaneously measured next to each other. And if you could see the picture, there's a waveform somewhere here. I can kind of vaguely see it. Again, low SNR. What you see is actually that those signals are quite correlated, but they're not sparse by any means. So sparsity is not there in the time domain. But there's correlation between spatial. You can see little phase shifts between different electrodes. If I can basically extract that, I can do interesting things. So you have to look at it in a 2D fashion. You say, this is an image I'm getting, a 2D image of what's happening at the brain. And if I basically start looking either in the frequency domain or in the time domain, I can do some interesting data extraction strategies. So it brings us all the way to machine learning and interesting type of signal processing applications. All right, bottom line, ECOG we can do. Now, let's go one step beyond that. As I said, the next thing I would like to have is a bunch of those electrodes that talk to individual neurons. And the more the better. Now, one thing I cannot do is have those electrode arrays, as you can see right now. If you basically totally fix the electrode array and you fix it to the skull, anytime I move my head, I'm going to damage my tissue. And that's what's happening. That's why a lot of scarring happens. So our idea is, what if I could make free-floating electrodes? Electrodes that are basically sitting in the tissue and move with the tissue. So that was one of the first experiments we did. We said, okay, let's see if we can do that. You have an electrode right here, like all the ones you showed. They could be flexible, they could be silicon, or whatever. And let's build an acquisition channel on top of that electrode that moves with the electrode and then sends the data to some interrogation device that sits like on an ECOG array. Right, so you have a little wireless link between the electrodes and the interrogator, which is just above it. The distance is very small, about 1 to 2 millimeters maximum. Right, that's all the distance you have to cover. And those things are so small that I actually can print the antenna on the die and integrate the whole thing together. So that's something we built. This is an example of a chip. It has 4 amplifiers, 4 electrodes you can do. It has the power management, the communication, all the same stuff that I showed on the previous chip, but no, on much smaller scale. This antenna is printed on top of this electronics. It's about 100, 200 micron, or 250 by 500 micron wide. Very tiny antenna. Very inefficient antenna, as you can imagine. For the frequency we're talking about, I have a lot of loss. So it turns out, yes, you can build this, and we actually showed this again. This is data from a rat, and it shows a really nice waveform measure with the free-floating electrodes. No more kind of fixed things that basically I can basically put in the tissue and then move with it. So that's really cool. Sure, that could be done, but it's not. We kind of realized it was not the right approach, because this thing takes about 10 microwatt. Now to get power to it from even only 2 milliwatt, the loss factor is so big that you have to basically pump in lots of milliwatts of power on one side to get 10 microwatt on the other side. It's very inefficient. You get heat problems and all those kind of things. So a good experiment, but ultimately you said, nah, that's not the way to go. So next step, we basically moved on. This is, let's think about, by the way, these things we call these free-floating electrodes, we started using a name for it. We call them neural dust. Little dust particles we put in the tissue, and they help us to measure signals. So this is our next step. It's well, I cannot basically get the power from the flex hub, from the hub node or the interrogator to the electrode, so let's have a compliant type of tether that basically brings them together. And you can do that. Here's an example of some of the technologies. This is your electrode right here, and here you see the flex cable that basically allows you to connect to your electrodes in a flexible fashion. The electrodes are still movable individually. They're not fixed into an array, but the advantage is I don't have that power problem. And then I can build, let's say, an in-my-body router. You call it that way, right? It's basically a system within below your skull that does 2 things. It gets power from the outside. It sends data back over a wireless link. And then you have a number of chiplets that basically do the data acquisition. Because now I have a cable, I can have analog signals coming in here. This is where you do the data acquisition and conversion and so on and so forth. So it's kind of interesting. You can start seeing now that this becomes a system. It is a combined of, you have electrodes on one part, we have wireless nodes, we have routers, we have power delivery systems, and so on and so forth. It really becomes a network within the body. So next step that we've been taking, we actually built a chip for this part, this little chip here. This is a 64 neuromodulation IC, which published just a couple of months ago at VLSI, where you have 64-channel data acquisition like normal, analog, A to D conversion. We have regulation. We also have compression. in terms of dealing with the neural data deluge, we said, well, why not put compression on these things as well? So you have a programmable compression unit on the die that helps us to reduce the amount of data I have to send out, which makes it scalable in terms of number of channels. So now you start putting basically signal processing. It also has stimulation capabilities. It allows you to not only measure signals, but actually put electrical pulses, current pulses at particular electrodes to basically close the feedback loop as I talked to you before. So that's basically what I mentioned. This is the compression part. So rather than transmit the complete waveform, if you can figure out where the pulses are by using some thresholding and nonlinear function analysis and things like that, I can not transmit the full waveform, but only the region around the pulse, which is called an epoch. All the noise around that basically we throw away, or the LFP we throw away. You can do that separately. The advantage of going from here to here, I go from 13.5 megabits per second to 2 megabits per second. If I don't care about the pulse at all, which is happening in a number of BMI, you really want to do brain-machine interface type stuff, neuroprosthetic type thing, you don't care at all about the waveform. You care about the firing rates. How often does a neuron fire? So if I can figure that out, I can reduce the bandwidth to about 10 kilobits per second, which you could do as well, fairly simple compression thing. Now, it depends what you want to accomplish. If you're a neuroscientist or somebody in BMI, you might want to have different goals. So where this is all leading? Well, this is our 5-year vision. We got contracted together with a number of other folks from UCSF, things like that, and New York University on a program which is called DARPA Subnets, which is basically looking at building of prosthetic devices and neuropsychiatric diseases. And this is kind of the device we're currently constructing. It combines a computer module, implantable. There's a little processor unit that does also the powering. We have a router device, a data aggregator, and implantable devices at numerous spots. They can be ECOG, or they can be deep brain type of node, or they could be type of right. So this router allows us to have a flexible number of implantable devices. And this is what we're currently trying to build. And even more, we're going even to the whole approval process, regulation process, to basically get this into humans within this 5-year time span. So it shows that this technology is really moving forward, and that indeed by basically bringing all those things together, really make some of those things happen. Now, is this the end? By no means, right? My dream is really to have this very scalable, flexible, expandable systems. So how can we go to these thousands of neurons, thousands to maybe millions of channels? How could you do that? We tried this a while back. I said, well, you have to make nodes that are really tiny. If I can make little cubic nodes that are basically 50 micron or something like that on the size, I can just spread them around in the cortex, a whole bunch of them. And then if I can wirelessly communicate with those things and power them, I get a lot of information. We tried it using electromagnetics about 5 years ago, did all the math, and like good engineer says, can't be done. Actually, the numbers just didn't work out. The loss factors with these very small devices were just too big. We got 2 nanowatt of power, which is nothing. We couldn't do anything with it. So we gave up on it. Till a couple of years later, we got a bright grad student come in and says, I have an idea. Why not replace the electromagnetic waveforms with acoustic ones? Use ultrasound. Ultrasound basically behaves a lot better in tissue than electromagnetics do. And actually turns out to have a larger wavelength, so even with smaller antennas, I get a lot better efficiency. And this is what led to this whole neural dust idea, where we have little cubes of piezo material. 50 micron on the side is really the goal, because that's really where the body starts saying, hey, this is fine. I don't have any problem with you at all. And it shows that if you basically go, let's say, to a 50 micron device, approximately, this is how much power you can get from an acoustic waveform. That's what you can get from electromagnetics. 3 orders of magnitude difference. This is rare in engineering, that I get 3 orders of magnitude. So this is really cool. When I discovered this, I said, hey, this is really an interesting idea we should pursue. So this is the vision we're building as another part. This is, again, further out, the neural dust vision, indeed, where you have little particles that are basically subsiding within the cortical region. And then you have an electrode array that sits on top of that, does the interrogation, and basically sends the acoustic waveforms in and get this backscattered signals back and turns them into real signals, which you can then transmit using electromagnetics to the outside. Actually, acoustic doesn't go very well to the skull. Electromagnetics do. Skull basically, the scattering basically, and the thing like that basically make sure that acoustical signals don't propagate very well. So this is what we're trying to do. Interesting engineering problem, how you build those little things. You have a little active transistor on those type of things. Very interesting manufacturing type of issues. Insertion problems. Whole bunch of analysis on how much data I really can get under practical circumstances. Interference between in neighboring nodes. All those kind of things are interesting questions. And then the last question is, again, you have the neural data deluge here. Lots of nodes. How do I even talk to an individual node? You put them randomly around. How do you know what you're talking about? How can you basically address one single signal? Again, we're signal processing. We know how about signal processing. We see what people have done in the world. So you might start thinking about, there's another slide here, basically just repeating what I already said. I get my 3 orders of magnitude. That basically analyzed, and we've shown it. Actually, we measured it now in a large kind of test bed. We've shown that exactly the theory matches the experiment. So 50 micron feasible for SNR of 10 dB, smaller possible, but we're basically, at some point in time, you get basically limited by the electrode noise. So again, the question is how to talk to individual neurons, or individual one of those devices. Well, again, we've learned how to do that. If I take my interrogator and turn it into an array, I actually can do anything we've learned about MIMO, phased array type things, to basically direct the acoustical beam by having multiple electrodes. You direct the acoustical beam in different directions. Or you look at the backside of the signals and receive it on multiple receivers, and you combine them together using signal processing. Again, this is well known. And indeed, you can see that if you have a particular electrode here, you can measure what the beam kind of looks like, and then you can start to figure out, should I have a lot of small ones, or should I use bigger ones, and so on and so forth. But I can do beam steering and all this kind of stuff. It shows indeed that if you do the right algorithm type stuff, actually you can get very good resolution and discrimination. So that shows it's possible. Challenge? Well, here are my neural dust nodes, and here are all my a lot of signal processing, a lot of computation. Where do I do that? Can I do that below the skull? Can I do this in such a way that I don't get a hotspot? All those type of things. Should I basically do it hierarchically? Should I move some of the data out of the brain and do the processing there? So interesting questions from a system design perspective. But again, nothing that fundamentally shows it cannot be done. So we're pushing really hard on moving this thing forward. All right. So I think the technology is moving forward very nicely. And I think, as I showed you here, primarily for the cortical interfaces, you can imagine the same type of things happening for the peripheral neural systems. There's a lot of different things happening, different technologies emerging as we speak. Now, at that point in time, it's worthwhile occasionally to step back a little bit and think about what's the overall impact of this thing. And when we published our neural dust paper about a year ago, right away, this got the popular press got an eye on this type of thing. And you basically right away start reading these things like, neural dust implanted in the brain may let minds melt with machines. Or the other one said, neural dust is spying on your brain. Right? So that's the next question you basically are getting. And obviously these are important questions to address. Right? It's not something we can ignore. Here it is. How smart, this is an MIT technology review of all places. How smart dust could spy on your brain. So again, this is something that I think we should not ignore. The fact that we start creating that capability, it requires that we start thinking about it. Is there certain ways to get around some of those challenges we see here? The other thing is that the mind of type of things that might be possible once you start creating these things is quite amazing, right? Here's a couple of, again, experiments that people have done. This is the group of Nicolellis at Purdue. Has shown that he actually linked 2 rats together that were in different parts of the world, one in Brazil and one in Purdue. Basically both rats had an interface. He took the signals of one rat, and typically the way these experiments work, the rats get a reward if they do a certain task. They get some juice or something like that. So they measured the signal of the single rat, basically while I was doing this task, and they took those signals and transmitted them using the internet to another rat in Brazil, and basically used that to stimulate it. And the goal was to have the second rat doing exactly the same function as the first rat, so they're coupled together. And to make it harder, the first rat only gets the reward when the second rat does it. So they make a feedback system out of the thing. And it kind of worked. They demonstrated this worked. Just this August here, there's another article. Could we send emails telepathically? A scientist transmits message into the mind of a colleague 5,000 miles away using brainwaves. It's actually very straightforward. It's kind of a little stunt. They took EEG on one pattern. They took like a Morse code. Think about black, white, black, white, black, white, right? You can make anything. You basically can make a code, and you can make a message and transmit it out, and then you can stimulate it out, take it out, put stimulation, and the other one can say it's black or white, right? So you can basically get the code back. That's really what they did here. But it shows what is possible. Right? This is primitive, but if you start just opening your mind and say, well, gee, we're moving forward, we're going to have a lot more sophisticated type of interfaces, all those type of things become kind of worrying and something you have to think about. So the takeaways is, I think brain-machine interface are, to me, the ultimate in immersive technologies and wearable technologies. It's something that, if you think about anything that I want to wear and can do, this is ultimately, wouldn't it be nice to be able to control things by just thinking about them? Wouldn't that be nice, right? Potential is huge. I think, first of all, it's going to be societal impact. Indeed, basically dealing with all those neural diseases. But you can never basically, human advancement is probably the next one. Number two is a new breed of integrated bioelectronic circuits are working. And a lot of people working on that. There's a lot of work going here. And not only on the BMI space, but any part of the body, basically. There's many, many different activities. And it requires rethinking of how we build circuits. It's not anymore a traditional circuit design or system design. We really have to think about the interaction. What the signals we need, what is the information you want to basically acquire, and so on and so forth. Signal acquisition or stimulation is only a small part of the story. How to get the real information out there and is very important, and think about that. And finally, as I already said, the global impact can be huge. Long-term repercussions is something we have to think about. Safety, security, and privacy. This was the Berkeley Engineer magazine, was published a couple of months ago, and it says we really should start thinking about our last firewall. If you have all those kind of devices on Earth, maybe wearable devices, implantable devices, how do you protect those things against people snooping in, basically people trying to provide malware, all this kind of stuff. Something to think about when you start going to this space. So that's it. Thank you for your attention.
Thank you, Jan, for quite a really interesting talk. We've got a little time for some questions. Any questions? Yeah.
Yes.
Thank you for the great talk. My question is about the tissue property during the long-term experiment.
Mm-hmm.
So when electrode array is implanted in the tissue, then I think the surrounding tissue, its property may be changed over the long-term experiment.
Mm-hmm.
And it may be hard to address this issue during system level or electrode design. So how can you handle this issue for long-term experiments?
So it's a very good question. It's, what happens if the signals basically change, right? That's the question. If you have an electrode and you measure signals basically over time, the signals can change, right? So a couple of things you can do about this. It turns out that a lot of the control algorithms that are used in BMI require some stationarity. They work while you train them. So you basically train a task, and they start doing that, basically start moving the arm correctly. Now, the signals change. Your training is going to get worse. Right? So you have to start basically thinking about the whole system. You say, well, maybe I can adapt to changes in my signals. I can learn about those changes and adjust my control algorithms to basically deal. The whole neural network will change as well. So there's this new philosophy now that you basically have to do adaptation at two levels. There's adaptation of the brain, and you have basically the adaptation in the electronic system around it. The second part is that if certain signals suddenly disappear, they're obviously useless, right? And that's why you need redundancy. If I lose a neuron, it doesn't matter. It turns out if I have a neighboring neuron, I can train that neuron just as well to do the same task. That's another thing that I was learned. You don't have to rely on a single neuron. You can actually remap the function to other neurons over time.
There's another question here.
Mm-hmm.
I would have thought your favorite sci-fi was Brainstorm, Natalie Wood's last movie.
Mm-hmm.
But speaking in that regard, I think they were using squid in those days without knowing it. Do you feel that imaging will evolve to the point where a CAP type of thing, which is purely non-invasive, the opposite of what you're talking about here, will be able to sort it out, much like your kind of phased array antenna thing is doing? And is there any work being done in this area?
Very good question.
So such as 3D imaging of the
right.
internal brain.
That's right. So obviously that would be, if you can avoid any invasive technologies, that's by far the more preferred approaches. And again, this is where some of the agencies are looking very deeply. And DARPA itself just announced a new project, actually it's called Electrix or something like that, which really is trying to figure out, can I do this whole thing non-invasively by using beamforming, but also using different type of acquisition strategies, different signals, combination of signals and things like that. At this point in time, I don't think there's anything that basically could be wearable, that you can walk around with, that basically can give you the resolution of the electrical ones. But I haven't said that I would exclude it. There's a lot of interesting ideas being thrown around, and maybe one of them will gel at some point in time. So I totally agree. This is the holy grail of where we want to go. Today, we're stuck with implantables, but I think in the longer term, we might want to basically look at, is it indeed possible to do 3D imaging using different modalities? But as I said, right now, there's nothing that can be on the wearable, flexible scale that we need today.
We got one last question back here, Jan.
Okay?
Science fiction question. I understood the antenna, it's a two-way street. Is there any security code so somebody else cannot control the so not the output?
Yeah, so a very interesting question. Can I really make those things secure? There's a variety of ways of thinking about it. I ultimately believe that we should start thinking about encrypting in one form or another every single digital waveform we ever transmit. It actually doesn't take that much energy to do some simple encryption on a stream. That's number one. I think that's, and we can basically find unique keys and all the kind of things, you can do that things quite nicely. The other approach is the fact that those signals are so small. Is there a way to basically shield them off from the environment that anybody else kind of coming around you cannot snoop onto them? And I think here in MIT, there was some work done a couple of years ago in the group of Dina Katabi on what's it called, human shield or something like that. But it basically on purpose generates noise around you. You create a field of noise around you that if somebody tries to snoop at you, the only thing they will see is the noise. While if I'm trying to look at a particular signal, I know the noise source because I generated it. I can subtract it and I get the signal back. So it's called active interference cancellation. This type of things are interesting ideas that could be used to indeed create that last firewall. So interesting directions again from a research perspective.
Okay, let's thank Jan again for a terrific talk.